We not only show a read oscillator-based VCO can generate multi-phase clocking easy, but also bring both the negative skew and FIFO delay cell to increase the oscillation frequency. Therefore, the high-frequency multi-phase read-based VCO should be able to provide the clock source for a high-speed SerDes functionality. Could you please tell me why we still need an LC VCO for the high-speed SerDes, even though it's not straightforward to generate the multiphase from an LC tank? Think about the jitter image for 5 seconds. Correct. The jitter requirement is very tight because of the high requirement on high-speed SerDes, especially the 224 gigabit per second. As you can see from the reference at Intel, the eye width is very tiny, which shows only 2.5 picosecond left at the TX output before the channel, because of the multiple crossover effect, which is discussed in the YNRZ SerDes video. Therefore, if the random jitter is higher, then the eye could be closed, which may break the link transmission or increase much more power overhead. We also know the LC VCO or PO may provide a much better jitter performance than the ring-based VCO. Then we must use the LC VCO for the clock source. But there's no multiple phase available easy from the differential LC VCO. What can we do? Think about a coupling images for 5 seconds. Right, if there's no multiphase from the LC VCO, at least we could have 4-phase quadrilateral phase of LC VCO. However, a simple differential LC VCO may have 2 phases. Therefore, we must have 4 outputs from the 2 LC VCO and do something between them to generate the 4 phases. Therefore, a straightforward coupling between both VCO is a must to pull the phase to be 90 degrees in between. Unfortunately, even though this LC quadrilateral VCO is feasible, there are still some PPA degradation. Could you tell me why? Bingo! First, the performance is the phase noise or jitter we care about a lot. In the beginning, we switched to the LC VCO instead of the original read oscillator. But to generate the quadrilateral phase, the coupling or pulling may degrade the phase noise or jitter is unavoidable. Second, 2 LC VCO are needed. Therefore, the power will be double. But the power overfed was the extra 2 phases generation instead of improving the jitter performance. Lastly, the LC VCO is already bulky in the area, and we even need twice the area overhead for the extra 2-phase generation. So that might give you some ideas if the LC QVCO is worth implementing in your SerDes. If you don't like it, what other options could you have? Great, a divide by 2 frequency divider is an option to provide 4-phase generation for you. In this frequency arrangement, the LC VCO may operate at twice the frequency, and the inductor can be helped to reduce the area a lot. So the overall area overhead is much smaller with a smaller inductor and tiny frequency divider than the previous LC QVCO. But is there any extra design change? Yes, the higher LC VCO may be sensitive to phase noise degradation, and tuning range can be narrow besides higher phase noise. What else? Right, the high frequency divider is very difficult to have a wide input locking range. Therefore, not only the twice frequency LC VCO will consume more power, but also the high frequency divider will be very power hungry. That's it. you can somehow mitigate the power or phase noise issue in your design properly. Do you still see an issue with the 4-phase LC VCO clocking for SerDes application? Correct. A narrow frequency range of an LC VCO cannot meet any data rate, even though for single protocol over different generations, like PCIe Gen 3 to Gen 5. Any ideas? Bingo! Remember, the PCIe Gen 5 is 32 gigabit per second, Gen 4 is 16 gigabit per second, and Gen 3 is 8 gigabit per second. Then you could just apply a different divide by 1, 2, and 4 frequency divider to generate each corresponding clock rate, but switch them through a multiplexer to extend the clock frequency effectively. Of course, because of the LC VCO frequency range, the whole frequency allocation is not continuous with the hole somewhere. As long as you pay attention to avoid those frequency holes in your protocol usage, that should be fine. But again, if you don't like this 2x frequency LC VCO along with the following divider, what else can you apply? Yes, you can just apply a simple delay line or phase shifter to get the 90-degree clock phase properly. But be careful, since the phase accuracy won't be precise enough from the poor-made implementation, you must add another quadruple phase error detection, such that you could trim the phase finely. Although this poor-made phase shifter looks simple and low power, it's still very challenging to get it precisely. Do you have another better option that probably can provide more phase instead of only 4 phases? Think about the delay cell images for 5 seconds. Bingo! We can apply a delay lag loop DL through a voltage control delay line VCDL to generate N-phase output precisely. Of course, the delay line may still have a resolution limitation since each delay cell has a finite or limit delay time. If your application wants to have the phase finer than the delay cell can provide, what should we do? Think about the interpolation images for 5 seconds. Correct, just add the phase interpolator PI after the DL. For example, the precise A-phase output from the DL and the PI after it can generate 64 phases, which could be much finer than the DL can support. Again, nothing is free, and please be advised that the PI is very power hungry and has lots of design challenges. For those circuit blocks, we haven't dived into it, and we'll come back to it if everyone is interested based on your feedback. Here are a summary of why you might need an LC VCO multiphase clocking for high-speed SerDes. The first eye diagram image of the PAM4 signaling from Intel shows you that the jitter requirement is very tight at high-speed SerDes, especially the 224 gigabit per second, which is only 2.5 picosecond I-width left at TX output because of the multiple crossover effect. Please be advised that Intel has LC VCO jitter about 100 femtosecond or below. If the random jitter is higher, then the eye could be closed, which may break the link transmission or increase much more power overhead. That's why we must keep the LC VCO multiphase clocking for high-speed SerDes instead of the poor phase noise in the read oscillator, which may not still meet the jitter performance with extremely much more power overhead. But there's no multiphase from a single LC VCO, and at least we should have 4 phases, quadruple phases, from the LC VCO. The first option is to apply coupling between two VCOs to pull the phase to 90 degrees in between, such that we join the four phases from the LC quadruple VCO QVCO. Unfortunately, people may complain about the design trade-off between the jitter and phase accuracy, in addition to the 2x power and bulky area. Then, secondly, people try to push the single VCO at 2x frequency with 1/4 of the area and a divide by 2 frequency divider to join the phase precisely. In addition, the multiple frequency divider can mitigate the nano frequency range issue of the LC VCO in a SerDes application. However, the design change for a high frequency target, either in the LC VCO design or the frequency divider, may not work or has lots of power overhead. So, thirdly, people even try another Pullman phase shift through a delay line or quadruple phase correction to reduce the power overhead, but the complexity and phase accuracy could be still a concern. Lastly, another option is to apply a delay lock loop DL through a VCDL to generate even more multiphase output, flexibly and precisely, to provide the finer phase spacing than the DL can support. We could even add the phase interpolator PI after the DL. Again, those approaches provide an extremely low jitter, wide frequency tuning range, and precise multi-phase generation I've known about. Feel free to let me know if you have other suggestions or ideas. I'm happy to discuss more circuit images here. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be better from it.